All right, let's continue our discussion on enthalpy. Enthalpy, we're going to shorthand as a delta H. And delta H here, our enthalpy, is our heat for a reaction normalized to moles. So we know that thermochemistry is the branch of chemical thermodynamics that deals with relationships here between types of energy within chemistry. And we know that when reactions proceed, very frequently energy is either released or it has to be added. And energy can be stored in a substance in the kinetic energy of the molecules or in the kinetic energy of the atoms within the molecules. Now we need to measure enthalpy or keep a track of enthalpy because we need to know how much heat is going to be required to do a reaction or is going to be produced when we do a reaction. Now, there's a number of ways of doing this, and one of the things is to define a term internal energy. Internal energy we're going to classify as a U, and we're going to say that U is equal to Q plus W, where W here is work. If the system absorbs heat, it's going to have a positive Q. If work is done to the system, that could be like compressing a spring, it's going to have a positive work, and it's going to get an increase in internal energy. We can also have a decrease. That would happen if the system releases heat, which gives us a negative Q, or it pushes against the system and does work, which is going to give us a negative W, where the total energy of our system is equal to Q plus W. But we can minimize work, which we like to do because we don't like changes of pressure and correspondingly changes of volume, by working at constant pressure. So what we do in chemistry is we work at constant P. Now, when we do that, we are going to look at enthalpy. Now, this is going to be an open container, which means that we're going to do this while we have a constant pressure. Q sub P, meaning heat at constant pressure, pretty much is going to approximate how much internal energy we have. So instead of doing energy, we just tend to do heat, and we are going to use it for our measurements. With here, our delta H, which is our change in enthalpy rather than just heat, is going to be Q sub P divided by moles. What this allows us to do with a nice open container and constant pressure, it allows us to remove work from our energy equation. Now, internal energy and heat are state functions. State functions means that it is independent of how you get to that state. So, for example, altitude or elevation. So if you are at the top of a mountain, in terms of your elevation, it doesn't matter if you are helicoptered in or you hiked up, your elevation is constant. It is a state function. That means it is independent of how the system is prepared. We're going to discover when we do the chemistry stuff, what it matters is what the state is in. And by state here, we mean solid, liquid, or gas. So it doesn't matter how we get to a solid, liquid, or gas, or the elevation as might be the case. What matters is the state that it is in when it's there. We are going to use equations to discuss this. So for example, if we want to look at the change in heat at constant pressure, and we're going to have to throw in moles here in a moment, we're going to have to start with the balanced equation. So we write our balanced equation and we put the change in heat on the right-hand side. Now note, this change in heat is associated with the reaction as written, meaning that we're going to have minus 286 kilojoules of heat produced for every 1 mole of hydrogen, or we're going to have minus 286 kilojoules of heat produced for every 1/2 mole of oxygen that is used up. So it's for the reaction as written. We can mess with this. So if we take our reaction, and if we take and reverse a reaction, so if we take this reaction right here and we switch it to two H2Os, or an H2O as a liquid goes into H2 as gas plus 1/2 O2 as a gas, If our reaction is reversed, we are going to get a change in sign, and our delta H for the reverse process is going to be positive 286 kilojoules. If the reaction is exothermic in one direction, it is endothermic in the reverse. If we happen to have more or less of something, so let's say we multiply this reaction by 2. If we do that, we multiply the enthalpy by 2. If we want half as much, we would divide the enthalpy by 2. How much heat depends on the physical state, which is why it's a state function. So we have to show which states they are. If we take it to a water, it's going to release more heat than if we take hydrogen and oxygen and just go to a gas. The states involved affect the amount of heat required to do the reaction, or in this case, produced when the reaction is done. If the reaction has a negative delta H, it's exo. Positive delta H is endo. If it's exo in one direction, it is endo in the reverse. But the direction's in the correct direction. And we can do some math for this. So if we take a look at this reaction, we have sucrose reacting with potassium chlorate, making carbon dioxide, water, and some potassium chloride. This reaction produces minus 5,960 kilojoules for 1 mole of sucrose for every 8 moles of KClO3. It would produce that amount of heat for every 12 moles of carbon dioxide produced, etc. So we have minus 5960 kilojoules of heat produced. Now I'm picking potassium chloride because that's what our question involves. We go to our balanced equation and we do this for 8 moles of KClO3. So the question is how much heat is produced when we react 7.19 grams of KClO3? Well, we know there's minus 5,960 kilojoules for 8 moles, so we're going to get the molar mass. There's 1 mole of potassium chloride for every 122.6 grams of it. We know that there are minus 5,960 kilojoules for every 8 moles. And when we do our math here, we're going to get minus 43.7 kilojoules. The amount of heat that is produced is going to depend on the amount of starting material, where the amount of heat is given is going to be for the reaction as written. So make sure you pay attention to your stoichiometric coefficients.